The Atlas instrument on the ICESat-2 satellite.
All right, that was your 1 minute of relaxation time. So before we get on to webinar, I want to all of us to have some great news here. Is that we will be having year 6 of the Trees Around the Globe Student Research Campaign. It was just approved by NASA and the Globe Implementation Office last week. So congratulations to all of you who put some good words in and continue to be part of the campaign. This is kind of unprecedented territory because there hasn't been a campaign that's lasted over 5 years so far. But we, as you know, we have great momentum. We have great representation at IBSS each year with an increase in student research projects related to the campaign. It builds up every year, so that's great. And with everything going on trees related, we have some folks here from trees around LAC, the Latin American Caribbean. We have trees across Ireland. We have trees around Israel. So lots of really cool kind of, I don't really like to call them spin-offs because these people are doing amazing things, and I don't want to attribute it all to our campaign, to the Trees Around the Globe Student Research Campaign. But we have these great campaigns in these regions. So we're super happy about these, and we're going to extend those, talk more about those throughout the next year. And next in September, we will actually in about 2 weeks on September 8th, and I have a shareable to show you in a couple minutes about that. But we have our next webinar. It will be the final webinar for year 5. And then year 6, we will have the first webinar in October. And we will also be talking more about year 6 and some of the plans at the end of next month's webinar, because we are going to align some of the things we do with the campaign to the, you may have heard of it, the Globe Year of Climate and Carbon, as well as the whole NASA Moon Trees program that is going on with the Artemis mission and all the way back to Apollo 14. So, but once again, we're excited to announce that the Trees Around the Globe Student Research Campaign will continue for at least 1 more year, so year 6, which begins the 1st of October 2023 and runs through September 30th of 2024. So this is awesome stuff, and we're going to bring more great science to you, great collaboration with some of the other campaigns, some of the spin-offs from the Trees Around the Globe Student Research Campaign, and lots of other cool things. So stay tuned for all that. We are working up some plans now, and Grace Crane Wright, who you know from the Globe Implementation Office, she will be speaking about the year of climate and carbon for Globe at our October webinar, at our first webinar for the campaign. So for year 6. So we're super excited about that. So today is going to kind of be a little more informal. We don't have a specific, outside speaker. We're going to be focusing a lot of it with our team and all you folks out here informally, because we're going to be talking a little bit about, well, a lot about biospheric research questions, a path to measuring the height of an individual tree to measuring the height of a forest. And we're going to focus on some really cool things, like some of the synchronized data that we get from different satellite missions. And Peter Nelson's an expert at that. But we're going to talk about some of the specific missions like ICESat-2 and JEDI and NISAR and SWOT and some synchronized Landsat Sentinel information. Because all of these, this harmonized data is super important, because you get those data sets from those different missions and you bring them together to paint even a much better picture, more specific picture of what we're looking at is when we're talking about tree height or land cover or greenings or anything carbon cycle related. So we're going to have a kind of an informal discussion throughout the day. A lot of it's going to be led by Peter, because as you know, Peter does amazing things with bringing the science of the the science that we do through the observations with GLOBE and the campaign, but also with the satellite data that we get and how to best interpret that data when you're looking at the satellite data and trying to do some like comparisons between different things. So we'll be showing some online tools as well. I'll be showing some open altimetry, kind of refreshing you with that as well. So I like this quote here by Tadao Ando. You cannot simply put something new into a place. You have to absorb what you see around you, what exists on the land, and then use that knowledge along with contemporary thinking to interpret what you see. It's kind of a good placeholder for what we're going to be talking about today with, analyzing and using different tools to understand, what's around you all the time. And when we do that, when we look at what's around you, we really look at that land cover around you. We look at those trees, what they look like, the tree height, all that information. So I thought this was a suitable quote to pop up here. And sorry about that weird .com address there. That was part of the original file, and I don't even know what that says. But it's really a terrible font. But I just kept it there because it was part of the original image. So today, the agenda, I mentioned a bunch of this, but we're going to talk. I'm going to mention a little bit about the Moon Trees Quest. Peter is going to pop on and talk about a little bit of what uncertainty means in measurements, because you've heard him talk about this before, from uncertainties to null hypotheses and all these things. Peter's going to talk a little bit about that, and then Peter Falcon's going to showcase a really cool story that he found about the West Coast called Zombie Forest. So very cool. And then we're going to kind of have a featured discussion, this informal discussion about looking at measurements of questions, looking at these satellites that I mentioned, looking at the harmonized data sets, a little bit about carbon sequestration and how you can figure out basically how much carbon a tree is taking in through some equations, things like that. So this is kind of like we're bringing kind of everything together here, and then we will finish up year 5, in a couple weeks when we talk more about bringing this data together. And then at the bottom here, we have something called the Biosphere research questions. And this is just some questions to think about while we're going over today's webinar, while we're talking about the things in today's webinar. So let me go here. Once again, we have great observations coming in all the time. We have over 36,000 measurements coming in just from year 5 so far. And total since the beginning of the campaign on the 15th of September, 2018, we have over 161,000 observations from tree height, land cover, and greenings from over 54,000 sites. So super excited about that. All right. Last part of the introduction. As you know, what's going on right now is the NASA Moon Trees Quest, and the official quest runs through the 21st of September of 2023. And remember, I know a lot of you are from countries outside the United States, but this is a U.S. regional quest because the majority of these trees are in the United States. There are some in South America, as you know, and there's a whole bunch around the world that may be second generation moon trees in different parts of the world, but they're not really documented. But with that said, as a reminder, we're looking at these specific moon tree species that were part of Apollo 14. So we're looking at people to find Douglas fir, loblolly pine, sweet gum, sycamore, and coast redwood for the Apollo 14 trees. Okay. On Artemis, they switched out the coast redwood and changed that to giant sequoia because coast redwood has such a limited geographical distribution. Giant sequoias have more, but giant sequoias are the cousin of the coast redwood. And then we actually have about 60 actual Apollo moon trees measured during this quest so far. So actual ones from seeds that were grown on board, that were taken on board Apollo 14 in January 1971, brought back to Earth, germinated on Earth, and then planted around the United States and in South America. But we have 60 of these that have been measured, actual Apollo 14 moon trees that have been measured around the United States since the beginning of the quest. So that is very cool. And this is all the different species of these trees. And I know Peter will talk a bit about, the Apollo 14 moon tree at Oregon State University in Corvallis. So I won't steal any of his thunder when he wants to talk about that. So One of the things I want to mention with the Moon Trees Quest is that we have reels, and if you're on Instagram, these reels have been posted in different spots on Instagram because we have all these partners. We have the Artemis mission, we have the USDA Forest Service, we have the NASA Next Gen STEM program. So we have lots of folks from different areas doing this. So there were a couple Artemis reels that were sent out, that were posted, and this was on the Artemis Instagram page. And then also a NASA Earth Instagram page grabbed these as well. So we have over 400,000 views. We're actually closing in on 500,000 views for these 4 reels. But I wanted to show you this last reel. This is the last reel with Dr. Erica Podest. Peter Falcon did the recording for this with Dr. Erica Podest at the Jet Propulsion Laboratory in California. But this is just an example of one of the really cool reels. And these reels, to go on Instagram and to become YouTube Shorts, they're about a minute long in length, but they get down to kind of like the nitty gritty of what we're talking about. So let me play this real fast.
Hi, I'm Dr. Erica Podest, a scientist in the Carbon Cycle and Ecosystems Group at NASA's Jet Propulsion Laboratory. I use satellite images to study trees and their role in the global carbon cycle. I'm here in Southern California next to this lovely sycamore tree, which is native to this area. Did you know that trees are the lungs of our planet? They take up carbon dioxide and provide us with oxygen. Most of that carbon dioxide is stored as carbon in the branches, leaves, trunk, roots. And knowing the height and diameter of the tree can help us estimate the amount of carbon stored in them. An important part of this effort is comparing on-site tree measurements with satellite measurements of tree height to validate what the satellite is telling us. And you can be part of this effort by participating in the NASA Moon Tree Quest and taking tree height of 5 species of Apollo 14 moon trees. So get out there, and I can't wait to see you ready.
So a lot of you may remember Dr. Podest from past campaign webinars several years ago, and then also she's been part of the GLOBE program for a while now with the GISN, and a lot of things with. She originally was doing a lot of stuff with us with the SMAP mission and the SMAP block pattern soil moisture measurement protocol. So Erica has done amazing things, and thank you for Peter for recording that and getting that to us. And this is out. This has about 20,000 plus views already. So we're super excited to see that. All right, so I'm gonna stop here. I'm gonna unshare, and I'm gonna pass it over to Peter. Peter Nelson, talk a little bit about the uncertainties, and then he'll pass it over to Peter Falcon, and then we will talk about the zombie forests of the United States West Coast. So let me go ahead and stop sharing and pass it over to Peter Nelson.
Excellent. Thank you, Brian. Let me just get myself arranged over here. Let's see, where am I in the world today? Oh, all right, wonderful. It's always fun to show up and see what virtual background I put myself in. And so here we actually have some trees, right? Like this is always kind of the fun little piece, right? I want to kind of highlight that, today we want to talk about not only individual trees and sort of their role in reference locations, because trees usually don't move. And so in theory, all these trees that we're measuring, we should know exactly where they are in the world. And this location piece is really the most important piece that we can do. It's nice to have the pictures, it's nice to have those height estimates, but in reality, if we do not tie it to the correct location on Earth, we can't do those things that Dr. Podest was talking about. We can't compare it to the satellite measurements. Or if we do, we have to think about that uncertainty of our measurement. Is it exactly in the location that we say that tree is located, as well as, are those satellite images in exactly the same location? And that relationship between where we are in the world and where we're putting our satellite measurements, and that how they work together, both have uncertainties. When you look at and actually read any satellite measurements, one of the first things that they tell you is, if you get a coordinate, how close to that coordinate is it in reality? And so there's a lot of math that goes on upstream of what we end up working with, either as a student scientist working with JEDI data or the ISAT-2 data, open altimetry, like Brian has shown us. Because he's mentioned that even though it shows one individual point on there, in fact, that point represents an area of 12 meters. And so, this is kind of one of these really funny and interesting things, that points actually represent area. And so even though we are reporting an individual tree at this location, at this coordinate, in fact, we have some uncertainty about that location. And to me, this is one of those sort of exciting pieces that does take us back to a bit of the beginning of the GLOBE program. And I'm trying to pull up my screen right here because hopefully many of you out there might have been trained initially in this thing called a GPS protocol, also known as a global positioning system protocol. And this was, you needed a particular instrument to be able to locate yourself on Earth. That location piece, again, is a part of our measurements. And so, the date and time is a measurement. Our location is a measurement. Our height that we're making is a measurement. And every single measurement is referenced to something else. And you can really geek out on and spend a lot of time going down this rabbit hole a bit of what are you referencing yourself to? Right? How do you know that what you are saying is the truth? When you make a measurement, how comfortable are you saying that that tree is, 20 feet tall? Because that's what I measured using the Globe Observer protocol, which has the app, it has that location piece, it has a date piece, it has a lot of those measurements already being made. And what isn't apparent sometimes is that uncertainty around those measurements, right? And so this idea of rounding, of what is, and even reporting our uncertainties of our measurement is something that we really want to focus on this year, because it gets into this idea of when we make a measurement, how confident are we in that measurement? And then based on that confidence, what can we say about it? And so, the Globe Observer mobile app actually has, depending on where you are standing and where you are making your angle and the type of angle, whether it is really acute or really small, or whether it's starting to get it to that 90-degree angle, all of those things actually affect the sensors that you're using to make this measurement. And that's why in there, Brian and others have said you should be no further away than 50 feet from, or 50 meters from a tree, right? Because as you get further away, our ability to have confidence in that height starts decreasing, okay? So, I want to really emphasize that I fall into this trap where I just report a number. But in fact, that number is an average of multiple measurements, or it is many, or it's a number, but it actually has some variation based on the engineering of that instrument. Okay, so GPS is one of those things that we used to really emphasize in terms of the location having coordinates. Yes, and that's an average of multiple measurements that are happening. And this is what happens, when you are using your mobile device. And I think the key here that I want to emphasize is that when you're using your mobile device and using the Globe Observer mobile app, sometimes you are using global positioning system to locate yourself on Earth. And sometimes you're using actually not satellites. You're using the Wi-Fi connections, or you're using the cell towers or other things like that to locate yourself, in addition to those GPS coordinates. And so even though, this was great at the time, this is one way of locating ourselves on Earth. And I'm really stressing this because it really gets into our ability to find that tree again. And you wouldn't be surprised very much, but a lot of our property records reference a tree. That is the corner of somebody's property boundary. And so these, knowing exactly where trees are located are really is vital for not only us understanding how many trees there are and having some confidence with that, but importantly, being able to combine that together with the satellite measurements, which also have that uncertainty with it. So I want to really highlight that this GPS protocol that Globe has, this was put out in 2014, but it is a very important place to start because when you are doing those measurements with your students, this is one thing that we want you to do. The other thing that was really highlighted in this GPS protocol early on is how a tree canopy cover can actually influence and change your GPS measurements that you are getting. There are radio signals coming down, and as a result of that tree canopy, like over here, if you were standing right underneath there, the view of the sky, the view of the satellites gets blocked. So this is going to be an interesting piece when you actually look at where your data ends up in reference to something else, is your actual location of your trees might be off because of the way that the Globe protocol is actually asking you to stand underneath that tree, underneath that canopy, in a place that we know has some locational issues related to locating ourselves. Okay, so this is why one single measurement is helpful, but it doesn't tell us the whole story, right? So I want to really emphasize that a single measurement is useful, but when we're designing or having and trying to map out our community or trying to actually understand what that measurement means, we really need to either have made multiple measurements, or we need to start looking at other locations that we can build a confluence of evidence that we are actually in the right location to use these coordinates for more purposes, to find and enrich our data like the way that we've talked about over the last 5 years, and we'll be going into in this year 6. Right? Because as we start thinking about, well, what other data can we use that has been measured in the same location? This tree is just one of those things. And I want to highlight, this is one of the nice things, is that once you're confident about your own location, about where your tree is actually located on Earth, then we can start talking about the attributes of that location. How tall is that tree? When was the tree planted? How much carbon is in that tree? How much carbon might be there in the future? And all of this does really go back to the really important idea of locating ourselves on Earth. Okay, and so we want the students to be able to kind of quantify that. So this is where there's opportunities to use a whole class and really nail down the position of a single tree by having everybody surround a tree and make a measurement of that particular tree so that you can see what the numbers are in terms of the latitude, longitude coordinates that are there. Okay. The other thing that I want to really kind of highlight that it comes up with the land cover protocol a little bit more, but you'll kind of notice, down here, we really do emphasize how that tree canopy influences our location. Okay. And I want to emphasize this because this is, again, something that Dr. Podesta kind of alluded to. But one of the uncertainties when we're talking about carbon is actually how many branches there are, how many twigs there are, how many leaves there are. And we can't measure every single one of those things. So we have to make an estimate about that. And so that automatically means that we have some variation around those numbers. We might have a lower number or a higher number that you could get if you went back and redid those measurements. So that all of these little pieces seem to a lot of people, like, really getting detail oriented, but that's our role of a scientist, is to not just report a number, but to actually describe all the things that go around that number that might influence that measurement, that could explain why we're getting the numbers that we are. And then we can start looking to compensate or to deal with that, right? So here, if you're trying to take a measurement underneath a tree, and we know that tree is blocking some of the satellite view, and our coordinates might not be exactly where it is because of this known issue, then one of the things that we tend to do a lot of times is go somewhere like outside where you don't have a tree canopy, something that would obstruct you, where you can get a clear signal. You can give yourself a reference point, right? And so there you can then reference yourself and be able to compare where that tree's actually located. So I want to emphasize that it's really valuable to not just make a measurement and report that out, but it's to look at it, is that measurement useful? Is it meaningful? And how does it compare to these other things? And is there an issue that I need to sort of deal with? And one thing that I really want to highlight and stress is this idea of magnetic north versus true north. This is, again, something that when we're trying to locate these trees, what is north? What is our reference location? And and again, we have this thing called true north, and then we have all of this magnetic north that we've used for our instrumentation to help us find and reference locations. So I want to really emphasize that you can actually set this up inside of your phone, and it is an option that we do not record in the Globe database. So when you are actually doing some of those things and we're getting numbers back inside of the Globe database, we really don't know if you're pointed at true north or if you're pointed at magnetic north. These are things that come into the uncertainty of even something as straightforward as what direction are you pointed and which direction is that tree, right? So there is this piece in here which I want to sort of give people permission to test this out. What is the difference between making measurements with Globe Observer and referencing yourself using that tool versus using this GPS protocol? And this all goes back to just trying to make sure that we have that tree in the right location, so that when we do go to the satellite data, we have confidence that we're talking about the same things, the same location on Earth. I spent more time on that than I was really planning on, but I want to really kind of emphasize how important this piece of locating ourselves really is. And don't lose sight that there is value to this, because the next thing that I want to go into is this transformation between your measurements that you make in the real world and then putting it into the Globe database. Because this is actually, when you step into the digital world, this is where this uncertainty piece really becomes apparent, and you really have to be thoughtful about it. And we've highlighted this with some of our data sets prior with it. So I won't go into some of those details. You can look at some of our past data descriptions that are out there. But I really want to kind of emphasize this to all of us, because here within our Globe program, this is only 9 years old. But to me, I don't see many people actually using a GPS. I don't really see many people sort of double checking that location number. So I want to encourage you to do that initially, because as you see inside of here, Brian keeps talking about like how many sites we've recorded. Well, this kind of goes back into that site definition and where is that tree located? What is the surrounding and what is the context that that tree is living in? So this piece of what do those numbers actually mean, I think is something that I want to really kind of stress in this upcoming year with our students and with everybody here, because everything that we're doing with NASA science goes back to where are we on Earth, and do we have confidence in the attributes that we're associating with that location. So I want to just see a quick raise of hands if you're still with me, but I want to see how many people have used the GPS protocol within the last year. Just raise your hand, and we'll just kind of do a little quick count. Oh, of course, Mike. Mike is the one who of course, I would expect Mike to be the one still doing this. Congratulations, Mike. I know, it's because you understand the basis of this jump from the physical world into the digital world. So I'm glad to see that Mike is the one that is definitely still doing it. So if you have questions about how to do this or what's going on, Mike's your man and your teacher, and would be glad to dive into this a little bit more with you, because it really is very crucial to things. I found this activity that Svetlana Darsh put together, and it's on the Globe website. And because we've used this a lot when we talk about measurements in science, this idea of this target, this bullseye, are numbers and measurements close to each other, or are they dispersed? How do we describe our repeat measurements, right? Or our measurements of a location or phenomena? Again, you can have low accuracy, and so you're not getting the right number, but all of your numbers are grouping together, right? So if all of your students are measuring that tree all at 10 feet tall, but from LiDAR or from some of our other measurements, we know that it's actually 15 feet tall, it's okay that all your students are getting the same measurements and we have that difference. It's just that now we can account for that difference, right? So I really kind of want to emphasize this, because you can see this happening in action when you are watching, when you hit the reset button in our Globe Observer mobile app. You'll actually see the re-averaging of these numbers for the location, and you will see yourself kind of move around and jump around. And so it is really important. And previously, we would ask people to spend about 10 minutes or so trying to move from whatever the heck this blurry thing is up in the upper left. Very interesting sort of graphic. Has some accuracy and precision issues. But we really want to try to get down to having really high quantifiable numbers associated with our attributes that we send into Brian. So I just kind of want to really emphasize that, this is something that doesn't have to be something that's just on a board. In fact, this piece right in the middle, where we're trying to get high accuracy and high precision, is actually that ISAT-2 photon location that Brian was talking about. This is that 12-meter beam radius that is out there, and we're trying to get all of our points inside of there, so that when we go to open altimetry, we're actually getting the same things. So I belabored that point quite a bit, but I wanted to kind of really emphasize that locating that tree in the right place in the world is maybe not as straightforward and not as easy, but that is a foundational piece that we do and need to do. And I'm going to quickly demonstrate a little bit, or demonstrate this one thing here, where if you actually go into and turn on, just say, the tree height locations in Globe, and okay, so we've got this. Okay, so first off, I want to kind of emphasize that it's really nice that, yes, we're a global program, and it's nice to get this global perspective. But first, we're looking at a thematic map. So somebody has already sort of decided the way the world looks to us, and so that may not be what we actually want. And I'd say in most cases, when we're trying to reference ourselves, a thematic map is not what we want. We want a satellite image. We want something where we can actually see that tree, right? Because a lot of those maps don't have trees on them or individual trees. So we need to dive in and turn on that satellite image. The world looks different at this point. And I want to really encourage that as we're thinking about this individual tree, this individual LiDAR measurement or height measurement or satellite measurement, the carbon measurement, all those things, we really need to zoom in. And it is when you zoom in that you start to understand the uncertainty of your measurement. And you just have to keep zooming in. And I'm not going to go to Portland. Let's go down here towards where there is potentially a moon tree. And there you notice, resolution differences. So that again is one of these things that plays into our uncertainty of our location is, when you're looking out at a certain altitude, looking down, the actual pixel doesn't have to be as correct or have as many decimal points as when you zoom in, and you start to notice, some of these things. And well, we don't have a moon tree there, Brian, do we? No measurements here of our Oregon State moon tree during this time, but what I'll really stress here is, wow, all right, this is going to be fun. I think I'm in the wrong spot. Yep, that's it. And so, so what I want to kind of stress here is that as you zoom in and get closer to human scale, we can actually see the locations of the top of the canopy. Okay. So, and here, this is just a really interesting piece between what we're measuring on the ground versus this satellite view. Nowhere are we actually asking you to get the width of the canopy. So when we're thinking about where our tree point should actually be located, it's going to be kind of interesting because it should be in the middle of a green canopy of some sort, right? But you will rarely be able to see the actual trunk itself, like we're seeing there. So there's just some uncertainty in terms of how we locate ourselves. So, as I zoom in on this location, I find it really interesting. Here is the coordinates that are recorded or being shown on this map. But which tree is actually getting measured here? I don't know. And so right at this point, I can't actually use this high resolution satellite imagery to understand this tree. It's in the wrong location. And it's that uncertainty that scientists are trying to reveal. So one of the things that once you put your data into the Globe database, the next thing is checking to see what actually went up. What attributes are there? And importantly, where are you placed on the Earth? Okay, so and this is where you can really get led into misunderstandings if we use the wrong coordinates, or if we don't actually think about that uncertainty of our measurement. Is it really here? Or is it in fact, here's our scale of 5 meters. When we do our globe measurement using our globe observer, we have you do the reset button, and this point could actually be anywhere within, say, 5 meters as our general rule. So it could be anywhere from here where it's located all the way to kind of this edge of the canopy. And it could be anywhere in this 5 meter radius area, right? So right now, if I just took this and went to Open Altimetry to get a satellite measurement, I could get something very, very wrong, right? Because of this locational difference. So you might be asking, okay, I see this problem. What do I do about it? I think that's the important thing is for us to not just recognize a problem, but then to come up with a solution that we as a community can do. Okay, so one thing is you can again, go out to the same place and remake those measurements and see if you can, by averaging and remeasurement, move that point closer to maybe where the tree is that you actually measured. The other way is, inside of here, I don't have a cursor right now anyway that tells me where I am. And so that's another piece where if I go in here and actually turn on the map grid, that gives me a grid. But then also you can see here, I have a latitude, longitude that I can use to locate where this tree is getting put on this map. Okay, so this is a way that you can then go in and find the quote unquote true location of that tree, really where those coordinates are. And so you might actually have to take your table of coordinates and make a new field that you go through and you actually find, based on this map you're referencing to, what the coordinates really are on the map. And so, who's right? Well, that becomes the fun science question here. There is no right answer. It's really quantifying it with a lot of measurements and then describing that variation around your measurements. And so again, decimal points give us a sense that we have maybe more accuracy or more precision of our coordinates than we really do. So, just because a computer can give you 8 decimal points doesn't mean that you should use those. And so, to me, this is the first thing that I always do after my globe observer measurements, is to go in and try to see where my tree measurement ended up. And is it actually on the tree that I measured? Or is it in a place that I now have to add an offset and create a new table that I can then use when I go to the satellite data that's out there. So, wow, I feel like I spent a lot of time kind of going through just like this simple kind of thing like this. But I have found personally, as I review my own tree coordinates and tree locations, I'll go in here and I'll look at this, and I'll get a number. I'll get, here it's actually telling me that, wow, okay, the accuracy of this location of this point is 40 meters. So even though it's showing me this location, it could be any one of these trees that are within 40 meters of this point. So it makes it really hard to know, am I talking about this tree in the middle? Am I talking about this other tree or this big giant tree in the middle? And these canopies can blend together in that way. So again, this is where a good beginning first step is making sure your data is in the right place to begin with. And then once you do that, making sure that the attributes of that location. So the tree height is reasonable and is what you expected to actually go up into that database. The date is correct. And then, finally checking to make sure that the photo actually ended up, right? If that was one of the things that you did. So I'm spending a lot of time just kind of going over like this basic, piece of things, because I found, as I have tried to, follow along with Brian's MoonQuest project and some of what we're doing there, we have a moon tree at Oregon State University. And so I'm really hoping that we can use this as a reference location. We know when this tree was planted. And I went down, and so we know when this tree was born. We know we've been having it measured throughout the time period. And so we can figure out a growth rate. We can figure out some of those carbon numbers. We can do some of those things because we have those attributes, and we can tie it directly to that location. Those coordinates shouldn't have changed over time. But that to me is why it's really important to be able to focus on an individual charismatic tree like this, that is distinguishable, because I have all this information that I can use to understand the single tree And then I can put the larger landscape that it's in into a little bit more perspective through the satellite imagery. So I've been having a lot of fun doing some remote sensing of our moon tree, which is right here in our LiDAR space. And so I've been trying to kind of use this, because here in 2010, we actually have a measurement of a tree. And I want to highlight that. Notice it's an integer value. They're not giving me 68.4 feet. They're giving me a round number. So that's another thing to kind of emphasize to our students, is that we want to be thinking about round numbers when we are measuring our trees, especially with Globe Observer. Rarely will you be able to get down to a half a foot and be confident about that. Brian might, because he's highly calibrated, but for the rest of us, I feel comfortable saying within a foot or 2 feet or something like that. But the only reason why I feel comfortable putting some boundaries on my own measurements is because I've done repeat measurements of that, and I've come up with the same number or close to the same number enough times where, at least for that one tree, I feel comfortable with reporting that canopy height. Now, one thing I'll mention that I found interesting when I found this data set in 2010. One, it's from 2010. So we didn't have the Globe Observer mobile app. We weren't a Globe partner yet at Oregon State University. And so who was keeping track of this tree? Apparently other people were, so they flew this. But this 68 feet was exactly the number that I got when I measured it using the Globe Observer app 10 years later. Okay, that automatically should sort of raise some questions about, well, okay, who's right here? If we're coming up with the same number, but they are years apart like that, that does indicate that there's something wrong with one of our measurements, or that we're underestimating one of those measurements. So again, I really get excited about science when I start comparing my measurements to something else. And it's that relationship that starts to bring meaning to what we're doing. Because why is there this difference? Could it be the instrument? Could it be the way that we did it? Could this tree have actually stopped growing or stopped growing up for the last 10 years? There's all kinds of questions that come out when I started just seeing my place and attribute to this particular data set like this. So I could keep going on about uncertainty and sort of describing this, but I'll end my piece right here by going to a particular map that I think is useful for those of us in the United States. But I want to indicate that this is the kind of data that NASA scientists, including Dr. Podest, is trying to produce globally. Okay, so and there's a lot of places that have regional land cover maps or biomass maps or carbon maps or other things like that. So look at this as just kind of this an approach to look at the data layers in this way, because the big thing that I want to emphasize is that there's a lot of data that goes back in time that you can use. And so paying attention to the year of the data is incredibly important. That can be a reason why you have some differences between your measurements and something else, that date. Then one of the other things, that starts to come up is, we talk a lot about land cover in here, but the measurements that we're using to estimate land cover can also be used to estimate biophysical measurements like tree height or the amount of above ground biomass, also known as standing carbon, or in the globe world, the carbon cycle. And here we really are focusing on that carbon piece. And so, I want to emphasize that, here, we could zoom in, and if we are confident about our particular location and we know exactly where our tree is located, you can actually use maps like this to get information about the history of that. And here we're seeing like an increase in carbon over time at this particular location. So you can start actually not making your own carbon measurements, because those take a lot of time. But if you can put yourself in the right place and you have some confidence that you're either here or slightly around there, you can go in and you can start having confidence in the scientific measurements that can complement what you are doing. And I'll emphasize that you're not going to do carbon measurements without first doing land cover and without first doing tree height. You need those to be able to get at the carbon numbers. So as globe and as people start talking about carbon numbers and biomass and that kind of thing, recognize the foundation is land cover and that vertical component of the vegetation. And so we really have set you up well for starting to think about this transformation between, say, land cover of a location, the tree cover or canopy cover in that location, right, that you would see from space, but then also turning it into these biophysical numbers of carbon. But importantly, it all goes back to our location numbers and our confidence in that. And I feel like I've driven that point home so much, but the reason is because when we start looking at LiDAR data, this is something that Brian has kind of hidden from us a little bit and says, hey, go out, make a measurement, and then you might be able to find a measurement from ISAT or JEDI. Well, this is the kind of pattern that those measurements are making. It is not wall to wall in the same way that a satellite image is. And so, so this again gets back into why it's really important to get that location right, because if you are not talking about the same place as these laser measurements, you can't use those measurements actually. And so we really need that location alignment as that first step to understand and be able to start working with all of the wonderful data that's out there. And my word, that went into a whole different direction than I planned on necessarily, but I hope that it kind of helped set the stage for how location really matters. And I can keep going with that, but I'm going to just stop right there because I think it's really important to kind of focus on that XY piece of our data collection, as well as that Z part, which is that height that Brian really is trying to get us all to actually quantify, which is pretty exciting.
Thank you, Peter. Yeah. So yeah, but that, you say you went off in a different direction, but you fit everything that we were talking about in this agenda. It's just we went around the agenda, but I think it all over. But I think it's good because it leads us into some of the things we want to talk about and what we're going to set up for the September webinar as well as year 6 of the campaign. So thank you, Peter, for that. We're going to do a quick, Peter Falcon is going to do a quick presentation. Just going to, a discussion, I should say, not presentation, about the zombie forests, because this is another way that people, they were looking at their environment. They were looking at, and they discovered these, by observing the land cover and trees around them. So let me pass it over to Peter, and then we'll go on from there then.
Thanks, Brian. The great thing about hearing Peter Nelson talk is every time he says a few, something, it triggers an idea and ooh, I have an idea for a speaker. It just kind of leads to more discussion and more ideas. So thanks, Peter. Yeah, one thing I wanted to share is, as we go through our news feed, kind of doing our doom scrolling, we often come up with something that's pretty interesting. And I found something that was new to me. And I shared with Brian and Peter, and they thought it would be a great idea to share with the rest of the community here. So I just wanted to share with you something called zombie forest, something I've never heard of before. Let me go ahead and share my screen so I can show you the article. Actually, I can put it into the chat as well. There's an article written by Stanford grad students, and they were doing some research about something called zombie forest. And this is an area in the Sierra Nevada, which is in California. And you can see an image there. This is the conifer forest. So we're talking about trees like ponderosa pine, Douglas fir, what else? Sugar pine, I believe. these are very iconic forests. When you think of like Hollywood movies, they often show these types of forests, right? And what they found was, as the climate is changing, not only is it changing, affecting our oceans, our temperature, surface temperature, the atmosphere, but it's also having a drastic effect on these conifer forests. And basically, when the temperatures rise, these forests can no longer live sustainably. They can't create new saplings, new seedlings due to the warming climate. And because of that, in a matter of years, these forests are going to be gone. They're not going to be able to be sustained. They're not going to be able to grow new trees. So as the article goes down, it basically says in this region, an estimated of at least a fifth of these conifer trees are now unsuited for the region's increased temperatures. And in about 77 years, that number is likely to double. So here in California, it's about maybe 2 hours from where I live. There's a lot of people that go here for enjoyment, live in the foothills as well. And unfortunately, these forests are going to be creeping up further and further up in elevation just in order to survive. So we're going to lose a lot of these forests in the coming years. And as I read further into the study, I saw this. Let me see if I can refresh this page. Okay, let's see if it works. It's another little, let's see. Come on, work for me. Of course, it's not going to work. Oh, there we go. Okay, so here is, let me do this. Here is some data from there. Once again, Sierra Nevada conifer vegetation climate mismatch. So you can see VG. Let's see if I can move the image here and close this out. There we go. So on the right-hand side there, you see the legend, which is VCM, which stands for Vegetation Climate Mismatch. And of course, this blue area here, this is California. This area, this is all the Sierra Nevadas. This is a mountain range. And as we go in and zoom in closer, we can see that a lot of the area that they studied is going to be affected by this vegetation climate mismatch. So the red is, of course, severe with 9%, where the pink is 11%, and then the light blue is stable. But as you can see, once again, those colors are going to be changing quite drastically in the coming years. And we're going to be losing a lot of these forests in these lower elevations as they try to creep up further and further just in order to survive. And then when you also add in things like forest fires, wildfires, we had one just about 5 years back called the Paradise Fires, which caused a lot of destruction in homes and in this forest region. Because of that, that's going to actually increase the amount of time that these forests are going to be disappearing in the coming years. So I just wanted to point this out and share this article with you, and in the hopes of sharing it. But also, I just want to point out one thing I read is since 1930s, this area, the California Sierra Nevada, has warmed an average of 1.2 degrees Celsius. So that's pretty drastic. So if you see anything like this in your area, something you would like to share with us, please send it our way. We would love to highlight this and talk to not only about the regions that we live in, but share what's going on in the regions that you live in as well, and see how climate is impacting the trees and landscape in your area. So I will go ahead and put these links into the chat box, and feel free to read the article and read the research paper that is included with that, as well as this neat little data as you can play with that as well. Okay. So with that, I'm going to go ahead and turn it. Yeah, go ahead.
No, I love this. This is great, because I think that this is something that you're right. I want to encourage other people to come out and when they see things like this, because now we actually have more maps. We have more predictions at locations. It's not just a prediction of like, oh, this will happen. You're actually showing us a place that we can go, we can focus our attention, and we can make our measurements. And right now, to me, this is that thing of scientists are giving us these predictions in locations, right? And so, to me, these are, if they're vulnerable places like this, those are places we should try to get to as a community and try to highlight and try to get those initial measurements so that we can be part of that monitoring of these vulnerable landscapes. And what I notice right here is it is those edges of the forests, right? It is actually kind of those places where it's easiest to do a tree height because you can stand on the outside. You're not like underneath all the trees and can't see the top. So, I really like that as a way of helping to give us places to go, because one of the questions I always get is, well, where should I make my measurements? And yes, you can do it anywhere, and that is valuable. But clearly, there are places that scientists have identified that are of greater concern than other places, right? We still want people to be taking measurements in the stable areas, right? Because we need that to sort of also check that they really are stable, right? Or also growing, trees growing is stable. But and so we need those two contrasting areas. It's really important. But I really like that you've helped to highlight how these maps are giving us some new tools to have the conversation, to really make our measurements meaningful in a way that hopefully in 5 years we'll be able to look back and understand, were these predictions right, or are they moving in that direction, and kind of what's happening with that. So
Thanks,
I really
Peter.
like that, Peter. Yeah, definitely, definitely. And so, like I said, I mean, I just really like this because this was something that wasn't available even 5 years ago within the Globe protocol, within the Globe program. And even though here we are in a NASA program, we try to find global products. There are a lot of these very localized, specific things that are coming out that we want you to explore, and we want you to share with us. And Anna mentioned in the chat about oh, I need a tutorial to access or download the Jedi data. And yes, Anna, you're right, you do. And that's one of those things that we want to be able to provide even outside of these workshops kind of for this next year, because our webinars, they're packed full, and we try to get as much in here as possible, get you the tools that you need, but clearly you can't shut me up sometimes. So I think with some of these tools, and even what you're showing us here, Peter, is some more in-depth workshops that would be a good 3-4 hours, where we can go from something like this and then actually dive in a little bit deeper into and give you the tutorial, Anna, to be able to access the above ground biomass data that is coming out of these new missions, and like the data set I showed you for the whole continental United States. If you're in the United States, we already have carbon numbers for you. You don't have to go out and make those measurements. We need to have you explore those and explore that data set, because it takes a really long time to do those carbon numbers. And so, we need that to me is how we can help everybody coming up this next year, because there are a lot of tools like this. So if you do come across something and you think it would be not only useful to you, but maybe you need a little bit more in-depth understanding of how it works or how to use that, please reach out to us, because we're doing our best to find the data sets that are coming out there. But there's also a lot of different ways that we need to customize it for your technology. And that is one of those things that is really hard to anticipate, and everybody's position is unique. So again, in this year of open science that NASA is leading, the idea is to try to not just have one way of doing this, right? So you have to go through a particular software package or even a particular method. We want to try to help you find a way and a path to this information in a way that you can actually use, and that your students can use, and that you can bring into your science fair projects. So let us know, and we'd be glad to help you get what you really need to be able to answer some of these questions, because it's really kind of nice when your data and your observations have context, have meaning, and it's not just because your teacher told you to do it.
Thanks,
Yeah,
Peter.
and that's one of those things that, as Peter mentioned, trying to find the right path to, looking at the data, analyzing the data, doing all that. That's one of the hardest things that we're having as a campaign, because as you know, when you go to look up NASA data, there are a lot of tools out there to look at that data. There's individual mission websites where you can grab the data from. There's the larger ones like NASA Worldview. There's ones for ISAT-1, ISAT-2 and JEDI open altimetry, which I'll show you in a second. But there's so many different avenues to go, and Peter Nelson, his discussion is invaluable because he's trying to fine tune that down to to those specific routes or routes to that data. And that's one of the hardest things, because as data is coming at us from every direction, and plus you have space-based data, you have airborne data, you have ground-based data, you have data, you have ground-based data where you're looking down, you have ground-based data where you're looking up, you have ground-based data where you're looking in all four cardinal directions of north, south, east, and west. So there's data literally coming from you from every axis, X, Y, Z, and beyond, right? So
Don't forget T, time.
yeah, time, everything, yeah. T, you got the temporal, you got the spatial, you got all this stuff. So yeah, so that's good. So we have about 20 minutes left in the webinar, but we just wanted to also go in and mention a couple of the satellite missions, and we've heard about these missions before, of course, but these are ones that we're going to focus on a lot over the next year, because as you may know, NASA is creating this NASA Earth Observatory, coming up with all these new missions coming out, and one of them is one that I know Peter works with his colleagues at JPL, NISAR. That's a mission that we're going to focus a lot on. You've heard already from SWOT scientists in past webinars from this year, the surface water topography. So we're gonna hear more about that. So a lot of these missions and what they're measuring, or what they're measuring now, some of them like JEDI and ISAT-2 and the harmonized Landsat Sentinel data, that's what they're measuring now. And then what these missions in the future are going to be measuring really ties into what we're going to be doing for year 6 by looking at the the year of climate and carbon, looking at the further moon tree stuff, looking at these tools that Peter's been mentioning, and focusing on what are the uncertainties, and I'm going to show you here something with ISAT-2 is with open altimetry, as Peter mentioned, open altimetry. And something that, as he says, I've been hiding from everyone, how to get. And I should mention though that it's unintentional hiding if it comes out that way, because I say that because, as Peter was mentioning, with the uncertainties, when you're at the base of the tree and you're submitting your data for a tree height, as Peter saw, it might not in the globe database, depending upon your connection, GPS, which is Peter was mentioning, the importance of GPS, is that it may not end up in the right place. We've seen people send tree height measurements in where they swear that on their phone it showed that it was at the exact spot, but then at some point, when we look at it in the database, it's like off the coast in the water, like 20 meters off the coast of a beach, and there's no trees right there. So that's something that we run into. I mean, that's just part of the how the technology. So we try, and this is one of the reasons why Peter is doing this as well, because he's trying to fine tune. As a campaign, we're trying to fine tune this information. And thank you, Anna, for wanting to learn more about the JEDI and how to do that data as well. So that's perfect, because we actually next month we have a speaker from the JEDI mission who is going to be presenting, Dr. Benjamin Poulter. So, but let me go up ahead and share again. Then I'm going to jump in real fast, and I'm going to pop into just ISAT-2 quickly, and then in the probably 15 minutes remaining, then Peter Nelson, I'll pass it back to you if you want to mention about the harmonized data set, what that means, and some of those other ones, and then and Peter Falcon, I know that you may need to jump off for something else at JPL, but if we get to it, just you can mention a little bit about NISAR if you like, and but as I mentioned earlier, we're going to be talking a lot about these missions coming in the next year for year 6 of the campaign. So let me go ahead and share my screen and pop back to the PowerPoint here. Oops, sorry, that's the current slide. So some of the missions that we're really going to talk about over the next year or so, and just kind of, and you've heard about all of these before. The Landsat Sentinel harmonization, we have, that's a harmonized data. We have ISAT-2, JEDI, SWOT, and NISAR. And I just want to show you, all about ISAT-2. I just have these slides in here for the heck of it. So, And this is, where I'm hiding the access to the data, right? So we have, I love that. It's fun. But we have this, this arrow pointing to this one photon. This is one that happens to be on my property in Maryland. You may have seen this graph before. I popped it up before. But I'm going to go into Open Altimetry and just show you, because I've been working on a presentation I'm doing for it's a group. It's the Institute for Retired Persons in Salisbury University. So they're like alumni from Salisbury University who are part of this group. But they have like lots of talks and science talks, and they hear about different educational things throughout the year. And I presented to them literally a week before everything shut down for the pandemic back in March of 2020. And they asked me to come back, and because they wanted to know some more about, specifically NASA Wallops, where I work and what the science is we do there with the airborne missions and satellites and ground validation for precipitation in the GPM mission. But they also want to know about, some of the citizen science stuff. So I'm going to be introducing the Globe Observer to them. But I'm going to go ahead and stop sharing this and pop back and pop into Open Altimetry, because I want to show you something, because where I'm doing the presentation, ICET2 dropped a photon just outside the door of where I'm doing the presentation. So let me go ahead and just show you this. I just want to show you this kind of a reminder. If you were at the annual meeting, you saw me do something like this with some of the things, some of the trees that I found in Denver around the Curtis Hotel where the meeting was, where we were actually able to find where ICET2 measured these trees, and then I went out and took observations as well, and we did some comparisons. But I'm going to go ahead and share this, and we're going to go to Open Altimetry quickly, just for a couple minutes here, because I have a lat long. I want to pop in here. So you should be able to see Open Altimetry right now. And I'm just going to click on this red box, Browse ICET2 Data. And you've seen this before, and you might have seen it doing look at the tutorials. One thing I want to mention here also with Open Altimetry is that the ICET2 data is coming in like a terabyte of data a day. So there's a processing time, or what's called a data latency. So the default calendar that pops up will showcase the latest date, or the most recent date where we have the ICET2 data from. And I understand this is old. This is like 10 months ago. Okay, so that's data. But once this processing starts kicking in faster, you will see that drop to, a couple months, and even down to maybe a couple weeks. So, and that's out of my control, ICET2's control. It's all a whole processing thing. But with that said, I'm going to just pop in a lat long. So if you go to this search or zoom coordinates underneath the magnifying glass, this arrow, you get the latitude and longitude here. So I'm going to plug in the and please note here that we're used to saying it latitude, longitude, but here they have it set up, and I've been trying for years to get them to switch it, but now I think it's just a moot point. They're not going to switch it. Put your longitude first, because if you put the latitude there, you're going to end up on a strange part of the planet that you're not expecting. So the location where I'm doing this, where these trees are, is here. So that's the longitude. The latitude it's going to be 38.3457. So I'm going to hit update map. And when I do that, it's going to pop that latitude and longitude into the center. And what you're seeing there is where I live. That's Salisbury, Maryland. Okay, that's the big road around it. That's called the Salisbury Bypass. Okay, it's also called the Crossroads of Delmarva. Delmarva is Delaware, Maryland, Virginia, and it's a Delmarva Peninsula. So, but what I'm going to do is I'm going to zoom in here. Okay, I can just hit this button here and zoom in. But what you're going to see here is you're going to see this red. Okay, you see this red here. This is one of the ICET2 orbit tracks. And sorry, it takes a little bit for the site to render, but this orbit track lands pretty close to where I'm looking. So the actual lat long where I'm looking is going to be right here in the center of the image. So I'm going to just click on this little red line here, and this is the orbit track, and this will show the dates when ICET2 was close by the location I'm looking for. So you can see here, the most recent one for here is July 25th of 2022. And you can see that we have a line of photons here. And what I'm looking for are ones to cross right over here. So I don't remember the exact date. I'm pretty sure it's I can't remember the exact date the one that actually fits in here. So I have to do kind of a trial by error till that pops open. because it's going to align directly above, and I apologize for that, but I don't remember the exact time when it popped over. I know it's there it is right there. All right. So it was July 28th of 2020. So this is where, and I'm going to, yeah, right here, you'll see in the middle, okay, you see that area with the parking area around it. That's the building I'm going to be presenting in. Over here, ISET2 dropped a photon, and when I went out there, I did an observation, and I realized that ISET2 actually dropped the photon with that 13-meter diameter footprint that Peter mentioned earlier. It dropped, hit the top of these 2 young trees. So what I can do is to figure out what this tree height is, the average of these 2 trees. I can hit that select a region up at the top, and this hatched area, hatch mark will open up, and I can just go around that photon, let it go, hit view elevation profile, and it'll tell me the ground elevation and canopy surface, but it'll also align it to what the average tree height is for those 2 trees that ISET2 was able to hit. Because I went out there, and these 2 trees are the only ones that sit there within that 13-meter diameter footprint. Okay. Now I should mention, and as Peter mentioned before, this is not exact, because when I go out and measure those trees directly, I'm most likely, I hate to say it, but most likely won't get that exact latitude and longitude uploaded to the globe database. So I have to use that uncertainty and figure out and think about those ideas that Peter mentioned earlier with his discussion about uncertainties and knowing where the latitude and longitude is. So that's one thing you can do, is you can then, go out there and try to match it up the best you can. Okay. We only have like 9 minutes left, and I don't want to go any further, but we're going to be talking about this throughout the next, the next year, about the different uncertainties and the data and all that as well. So, let me go ahead and stop sharing, and I'm going to pass it over to Peter Falcon. Are you still there?
Yep, I'm still
All
here.
right. All right. Do you just want to quickly mention NISAR, and then we can have Peter Nelson finish it off till 1/2 past the hour, or for you folks like Yashraj in India at the top of the hour. So
Of course,
just
yeah.
want to meet NISAR a little bit.
Yeah. So NISAR is a joint collaboration with India, with ISRO, which is India, and we're going to be launching in January. This is an instrument that has a lot of different science objectives, from measuring natural hazards to terrestrial, what I forgot, was it water mass or something had to do with water. So sorry, I don't have my little science book in front of me to read all the different things that it's going to be doing. But we thought, it'd be great to bring in a speaker at some point during the year. I went to the science team meeting recently and found out that Erica Podest is actually on the science team meeting. So she'd be a great person to bring in to do a discussion about NISAR. And the great thing about Erica, of course, is that she's from Panama, so she speaks Spanish. This would be a great opportunity to get more of our Latin American community involved, so they feel more comfortable asking Erica questions in Spanish. So I just want to spread that out there. But let me discuss with her availability, because I know right now she's in the Amazon doing some field work. But NISAR is the next big mission for us. So we really like to highlight that and really like to bring that into the fold of what we're doing with trees and land cover as well. And that's about it, Brian. I think you're muted, Brian.
My bad. Sorry, my phone was going crazy earlier, so I had to mute quickly. So to set us up for next month's webinar, like I mentioned, it's going to be, and I'll pop that up right at the end, is going to be on actually on a Friday. It's going to be on Friday, the 8th of September, and you may have gotten the invite I sent out, I believe, yesterday, because that's when our speaker has the availability to speak on JEDI. I should say two speakers going to be talking about it, about JEDI, and we're going to be talking about that a combination, that harmonization of data, which will lead us into that whole multi-data, information we're going to talk about for year 6. So yeah, so what I'm going to do is I will now pass it over to Peter to finish up, talk a little bit about the importance of like the harmonized data sets, and then we'll take it from there.
Excellent. Thanks, Brian. Let's see, I am unmuted. Good. All right. So this idea of merging data sets is really important, because we've highlighted, if you just use one satellite that has its path kind of similar to what I'm showing here, you miss things, right? Like Brian was just showing. Sometimes you don't make the measurement on the tree that you actually meant to. And so this idea of bringing together the multiple measurements of remote sensing to better understand and quantify and characterize that location is really what the next 5 years is going to end up doing. And I think one of the pieces that I want to really highlight is that previously, we can get a lot of time measurements. We have some satellites that are out there that do every 15 minutes they'll make a measurement and capture an image of part of the Earth. And then we also have the detail piece, which if to get the detail to actually see those individual trees, we need to not actually go as often, which is why ISAT-2 kind of has a 4-month repeat time. It takes a long time to actually get those details. So the idea of building constellations of satellites is something that is becoming possible. And so the last number of years, it's been really exciting to see a lot of science going towards building constellations to trying to overcome and gather time data, which allows us to do tree phenology, right? Like that's one of our big measurements. That previously the only phenology data that we could really get was 250 meter pixel or 500 meter pixel. So that was averaging a lot of grasses, like I was showing, like what's behind me, and not getting as much of the tree phenology. And so one of the things that has happened over the last year is NASA, as well as the European Space Agency, has come together to merge 2 different satellite products, the Landsat mission together with the Sentinel-2 series of satellites. And they're very similar. They both do optical imaging. And what's nice about that is now we can actually get, instead of taking 16 days or 8 days to see the same location, this new data set that you can actually find in NASA Worldview, so you can visualize it and see it really quickly, is now available to us, which gives us the ability to see 30 meter pixels of phenology changes. So as we move towards the leaf off or the green up or green down part of our sort of campaign here, which our European phenology campaign has done a great job in, this is a new data set that actually can help us nail down the timing of that event. And this is something that wasn't really possible before. And so you can actually go through and there's a little bit of a lag, but what I love is here, let me turn that off. So this is the high resolution imagery. Notice that there's strips and that it's not the same as our MODIS data, which gives us a lot more. And that MODIS is what you see in the GlobeViz system. But here we actually have the ability to zoom in on particular locations. The other thing that I'll highlight that got added to Worldview that helps us in the GLOBE program is the MGRS grid. So this is the beginning of the site name, right? 10T or 11T or 12T. That is actually the site name. So that's available there now to help us start actually combining together and understanding our location and that site name together with the satellite imagery. So this is, kind of, for me, really exciting that here you can actually start zooming in and getting greater detail than you previously had been before. And so this is now available to us where we can actually get to very consistent, not quite daily coverage, but you can see that we move from having every 16 days to a lot closer and better. There we are. Repeat time at this higher resolution. So we can actually hopefully do a better job of watching the green up, green down of the tree phenology, not only in the fall, but also in the spring period. So, you know, this is something that I want to focus on because it allows us to finally get the details related to the tree measurements you guys are all making. So we'll dive into this a little bit more deeply, but just recognize this NASA Worldview allows you to start getting at some of the data sets that we want to highlight this year. And this phenology piece at 30-meter resolution is coming out right now. And this is the exciting thing that students can actually start working on, that is brand new science that nobody else has really looked at before. So those are just some of the things that we want to really highlight in terms of our data and opportunities that are coming online, you know, because of these new opportunities that NASA, working together with the global community, is being able to provide to us. That is really exciting, and hopefully you'll let us know what you need, and we'll be able to tap you into some of the new things that are happening in the computing, but also the data world, that your students can use and be part of.
I think that's one of the most important things that you said, Peter, is that, and what Anna has already done in the chat, let us know what you need, because we're here for all of you. Okay, we're not just here to do webinars, you know, every month just to hear ourselves talk. You know, we want to hear from you guys, because you're the ones who are working with the students, you're working with your globe regions, you're working with the scientists in your areas, and you're doing research. Some of you are doing research yourself. I know Yas Raj has been doing research for a long time now. So, you know, please let us know what you want. You know how to get a hold of us. You have our emails. You can bring it up during a future webinar if you like. That'd be perfect. But yeah, so definitely let us know what you need. And if you find something is difficult to access, or you just need something fine-tuned or something like that, you know, one or all of us will be able to do that. With that said, we are at time now for the webinar, but I'm going to pop up one last thing, and this is for our next our webinar next month. Let me go ahead and do this here. All right, so our next webinar, and as I mentioned, please note, it is going to be on a Friday, the 8th of September, 2023, so just over 2 weeks from now. It's going to be State of the Trees, September 2023, and this will be the final webinar in year 5. So this is called the Data Escape Hatch, and that's something that when Peter Nelson and I were talking about some of the planning stuff we were doing, you know, that's something that he brought up, and I really like that term. I figured out how do we use it as part of the title. But the Data Escape Hatch, so looking at data and how data fusion, which you've heard about today, you know, looking at the harmonization of data and everything, can help us understand our local to global environments. And we are going to have a featured discussion on such data fusion of old growth forest research, a combination of data from the U.S. Forest Service and the JEDI mission. And this is going to be with Dr. Ben Poulter and his colleague are going to be presenting at this. So I think this is going to be a great webinar for us to set up, you know, the whole data thing, what we want to do for year 6. Looking at the satellite data, looking at the data fusion and synchronization and harmonization of this as well. So, you know, please join us. And as I mentioned, once again, we're so used to doing them on Tuesdays, sometimes Wednesdays, but Friday was the only time that we really want that our speakers could be there, because they are always out in the field doing research and gone often. So this is the best time for them. And once again, this will be the ending of year 5, and we'll begin year 6 in October. So we don't have the dates for the October webinar yet, but this will be, you know, the final one in year 5. So thank you, everyone. Thank you, Peter Nelson, Peter Falcon, and everyone for your questions and discussion here. And I will stop the recording right now.